Alright, so today we're looking at a topic which I believe is called the radical of a nilpotent algebra. That might not be precise though. It might be a different topic. I will cross-verify to check that. But it's introduced here as the largest nilpotency ideal of representation. And we start out with a lemma here, which states we let G be a Lie algebra with ideal A and simple G module M. So keep in mind M is essentially a K module, but with this representation there's no stable non-trivial substructures in M. If for all x in A the action of x on M is nilpotent, then the action of x on M is just 0 for all x in A. Now let's look at the proof. Let N and M be the subspace consisting of M elements M of our G module M such that the action of x M on M equals 0 for all x in A. And so we essentially want to show that this N is just all of M. Now we have by result, which I need to check out what they're referencing. Okay, by Engel's theorem, there's an element which has this property, which means N is going to be non-zero. It's not just 0. We see for all y and g, N is stable under these ym. Hence, because M is simple, then N has to be all of M. And we're done with that lemma. Go immediately into another lemma, as you do. G is going to be a Lie algebra. M, a G module. Of finite dimension over K. Which is the base ring. I think it might even be assumed to be a field in all of this. And M has a Jordan holder series. I don't remember what that is off the top of my head. I'm going to look it up. Of Mi from 0 to some n. Now what is a Jordan holder series, you might be asking me? A Jordan holder series... Oh, it's just yeah, I remembered. It's just a composition series, so it's a bunch of like quotients of like things such that each quotient is like irreducible in some sense. Now we have the following are equivalent. A, for all x in a xm is nilpotent. Right, I'm guessing A is just an ideal of M as before, because they didn't redefine it in this lemma. Also, this would make more sense to be a colon and not a comma. B for all x in A. Okay, xm is in the Jacobson radical. Of the associative algebra A generated by 1 and the y actions of y on M for all y in G. And condition C is once again for all x in A. We have that the action of xm on M0 is within M1. I guess we have it of being of each relevant x of each mi is contained within mi plus 1. Under these conditions, oh yeah, they do mention that A is an ideal. With ideal A, under these conditions, A is orthogonal to G with respect to the bilinear form associated with the G module M. So the version of the killing form on M is everything orthogonal. Now, once again, if you're like me, you might be wondering, what is a Jacobson radical? Okay. The Jacobson radical of a ring R is the ideal consisting of all of those elements in R that annihilate all simple rate R modules. If the ring is commutative, it's equivalent to the intersection of all maximal ideals. And so examples for the ring of integers, the radical is just the 0 ideal. For a formal power series, the Jacobson radical is just power series with a 0 constant term. For the ring of all upper triangular n by n matrices, it's the ring of all upper triangular matrices with zeros on the diagonal. So that kind of checks out. Let's look at the proof. Well, B implies A first off. As A is finite dimensional, over K of course, the Jacobson radical of A is a nilpotent ideal, which I guess is just a result you're expected to know. And hence, so is every element. Or I guess that's kind of by definition of a Jacobson radical. Alright, A implies C. Every element is nilpotent. Show that xm of mi is an mi plus 1. So we start out with each qi equal to mi over mi plus 1 is a simple G module. For all x in A, the endomorphism xqi, which is derived from xm by restricting, which is just passing the restriction of xm onto mi to the quotient. Is null, and this is nilpotent by part A, and hence 0 by a previous lemma. Which one are these talking about? The first one. If for all a, xm is nilpotent, then xm is 0 for all a. By our first lemma of today. So that gives us that unfurling the quotient, xm of mi is in mi plus 1. If you restrict this to mi, it doesn't change it, and then by quotient means that you're dividing out that image, yeah. And lastly, from C to B, so in this case we have condition C holds. So each xm of mi is in mi plus 1 in our Jacob Holder series of m. And how do we get that xm is in the Jacobson radical? Well, so we're going to pick an x in A and a z in capital A as, I guess we'll use then z of ai of mi, sorry, you keep in mind that z.a is generated by 1 and the actions of elements of G on M. So we can either have that as a combination of scalar multiples and our representations. Z of mi is inside of mi, so that z composed with xm, the power of n, on capital M is 0. Because keep in mind m is finite dimensional. Thus, a times xm is a left nil ideal of A. I guess that just means it's nilpotent and an ideal. I will double check. And hence, well, yeah, I mean, it has to be based on what we have, is contained in the Jacobson radical of A. Now, finally, when A, which is same as B, which is the C holds, we had this last bit that A is orthogonal to G under the M version of the killing form. So we're going to let X in A and Y in G. Then ym xm is nilpotent, as we know. and hence the M killing form is just a trace of the matrix forms of the actions of ym and xm. Take their product, take the trace, and that is going to be 0 by nilpotency. And we are done. So, okay, yeah, I think we might be able to finish off nilpotency today. Maybe some cleanup. Okay, now proposition. Let G be a Lie algebra M a G module of finite dimension over K and A as before. That is, it's the associative algebra generated by 1 and the set of representations of elements of G on M. Then there's 4 parts to this proposition. A, the ideals A of G such that xm is nilpotent for all x in A are contained in 1, which we're going to call N. I'm pretty sure this is called the radical of the nilpotent Lie algebra, but they don't list that directly here. They just call it the largest nilpotency ideal, so we'll stick with that for now. I will cross-verify probably at the end of this video. B. This ideal N is the set of x and G such that xm belongs to the Jacobson radical of A condition C let mi from 0 to n be a Jordan-Holder series of M as a G module. Then N is the set of x and G such that the action of x on passed by quotient to mi over mi plus 1 equals 0 for all I. And D is that n is orthogonal to G with respect to the bilinear form of rho. The proof is pretty easy, actually. The set of x and g such that xm belongs to the Jacobson radical of A described in B is clearly an ideal, because I mean, like, think how it acts by bracket or sum or anything like that, it's obviously going to be stable. So we have condition B here, and then everything else is just plugging that in to our previous lemma, because it satisfies B, obviously. Then condition C here is C from our proposition. Condition A follows from our proposition, and from our A, and then condition D is this post thing in our condition. So that is actually the entire proof, which looks out of context kind of just like, yeah, it's obvious, but we did all the work in our previous proposition, or lemma, or whatever that was. And we define this n is called, we call it here, the largest nilpotency ideal. Largest nilpotency ideal for the G module M or for the corresponding representation. Now, so clearly n contains the kernel of its associated representation, but they are only equal when its parent module M is semi-simple, which is a concept we will see eventually, not right now though. I guess they are equal. It might, I don't know, it might be equal in a different case, but not in general is the key here. It should be noted x in G such that the action of x on M is nilpotent does not necessarily imply that x is in M, because keep in mind G is only the largest ideal. I don't know if there's like possible for other representations in subalgebras that are not ideals. So it doesn't contain every nilpotent element, it contains every nilpotent ideal. We also note from our lemma, which is what we use to prove all that stuff about the largest nilpotency ideal. This gives us another proposition, which is just a consequence of that lemma, and so we will not be we don't need to go through a proof. Let V be a vector space of finite dimension n over k, and G of the general linear Lie algebra V a subalgebra whose elements are nilpotent endomorphisms of V, then there exists a decreasing sequence
she's not available right at the moment. Can I get her to call you back?
of vector subspaces V0 all the way up through Vn of V of dimension n through to 0, such that x of Vi is contained within Vi plus 1 for all x in G and obviously for all I. Okay, and there's too many topics we have to cover, and we'll be done this discussion of nilpotent Lie algebras, and then I'll cross-verify with the other text to see if there's anything important we missed. But yeah, next topic, here, the two small ones here. We have the largest nilpotent ideal of a Lie algebra. Alright, so we let G be a Lie algebra with ideal A with ideal A, then A is nilpotent if and only if for all x in A, the adjoint representation on G of x is nilpotent. It is sufficient because of like everything we've seen so far, it is necessary because if A is nilpotent and x is an A, then the adjoint of x on A is nilpotent, and the adjoint of in G on G of x acting on G as a set is within A, which gives us that and the adjoint of G of x is nilpotent. Because essentially you just add 1 to the number of times you iterate it. Then, from our previous proposition, not the one immediately above, but the one where we defined the largest nilpotent ideal. Applied to the adjoint representation of G, we get proposition. G is a Lie algebra. Let E be the associative subalgebra of the linear maps on G generated by 1 and the adjoint representations on G of x for all x in G. We're going to let R then be the Jacobson radical of E. Then we have two consequences, A N, our largest nilpotent ideal of G, is the set of Y in G such that their adjoint representation on G of Y is in R. B, condition B, is that N is orthogonal to G under the killing form.
Yeah. Well, they do too. But yes.
And like we said, this is just our previous proposition defining n applied to the adjoint representation of G. So the proof is automatic. Note that the quotient of G over n can have non-zero, nilpotent ideals. And we have one more topic, Sporbachis. You know what this is going to be? It's going to be extension of the base field, as you do. Let G be a Lie K-algebra, K1 an extension of K, and G prime be the extension of G. As the kth central series term of G prime is the kth lower central series term of G extended to K1, then G is nilpotent if and only if G prime is nilpotent. Now, we're going to let M be a G module of finite dimension over K, with N being the largest nilpotency, as we saw, since ideal of M and M prime being the extension of the base field of M to K1. We're going to let Mi from 0 to N be a Jordan-Holder series of the G module M. Then the image of our Mi under X M is in Mi plus 1 for all X in N, as we saw. Hence that the image of, we're taking X prime and M prime, acting on Mi sub K1, the extension of Mi to K1 is contained within Mi plus 1 extended to K1 for all X prime being in the extension of the n to k1. Hence x prime m prime is nilpotent for x prime in n sub k1, so that the extension of n is contained in n prime being the largest nilpotent ideal of m prime. We show that if k1 is separable over k, then the prime of the nilpotent of the extension is just the extension of the nilpotent. As always, let E be the associative K algebra generated by 1 and the representations of x on M for all x in G. E prime is going to be the same definition for x prime in G prime. And R prime, the Jacobson radicals of E and E prime. With E prime canonically identified, with the extension of E. So that more Jacobson maths that I am not familiar with, this implies that the R prime is the extension of R. Going to let Y prime and N prime as the sum of some lambda I yi's for yi in G, because we'll take the sum of n of these. And lambda i's in K1 linearly independent over K. And then ym prime, y prime of m prime is the sum from 1 to n of lambda I times the extension of each yi to m prime and we have that y prime m prime is going to be in r prime, which is rk1. Hence, yim is in R. So each yi is in N. Thus, y prime is in the extension of N. So N prime is contained within the extension of N to the k1. That's our proof. In particular, if k1 is separable over k, then our largest nilpotent ideal of gk1, which is N prime, then I guess I'll write it out as they do. The largest nilpotent ideal of g extended to k1 is derived from that of g by extending the base field. And that's the end of our chapter here on nilpotent algebras. As I said, every text seems to have some conversation about nilpotent algebras, so let me just check that there's nothing too different or unique. I guess two concepts I will mention here real quick. If V is a vector space with a finite dimension, a flag is a chain of subspaces zero being the bottom one is contained within V1 all the way up to Vn being V, with the dimension of each Vi being I. So this is the same concept as we used before, where each kind of subspace slots into the next with the difference by adding a new dimension. Okay, the radical is the concept in solvable ideals, it looks like by here. They don't mention anything about the largest nilpotent ideals. They have that every ideal of nilpotent algebra must intersect the center, which I believe we saw. What about Sarah? What does Sarah have to say? Yeah, Engel's theorem proves it by flags. Okay. You know what, there's one more topic I found here. Most of this is pretty derivative. There's one topic I found that's interesting. I think we'll go over it here and then we'll call it a video. Not that it hasn't been long enough already, but still. Bonus topic. We're going to be translating Engel's theorem to groups. So we're going to let V finite dimensional vector space over K. An element G inside the general linear Lie group, not algebra, is called unipotent if it satisfies these equivalent conditions. So it satisfies all of them or none of them necessarily. They don't prove that they're equivalent, but here we go. Well, first off, it can be that G is equal to the identity matrix plus some n, with n being nilpotent. In some coordinates, G is a matrix with all ones on the diagonal and zeros below, no discussion of what happens above it. And condition C, all eigenvalues of G are 1. And looking at it, it's not too hard to believe that these are all equivalent. And here's our theorem. Which they attribute to Colchin. Let G be a subgroup of the general linear Lie group of V such that each G in our subgroup G is unipotent. Then there exists a flag f of elements Vi and V such that G leaves each Vi stable. What this means is that there's a coordinate system where all elements of G are triangular matrices, which by our above hypothesis will also have 1s on the diagonal solely. Now the proof of this. My induction on the dimension of V, if we can show that under the given hypothesis, so say follows by induction on dimension V if for V equals V not just being 0, there exists a non-zero V in our V, which is non-zero fixed by G. Now the equation of G minus 1, which is going to be some nilpotent n, times V equals 0 for G and G are linear, so have a non-trivial solution V over K, V over this K over our base K, if and only if they have a solution over K's algebraic closure, which we can go ahead and rate as K bar. So we may suppose K is algebraically closed. Now replacing V with a G submodule, we may suppose V is a simple G module. By Burnside's theorem, the elements of G span all of the K endomorphisms of V linearly as the sum over G and G of KG is a K subalgebra of the endomorphisms on K of V. Now we see for each G equals 1 plus N in G, we have that the trace of G is linear to the trace. I'm sorry, I should rewrite that. The trace in V of G splits linearly into the trace in V of 1, which is obviously going to be 1. No, it's going to be the dimension, I believe. Plus the trace in V of some nilpotent n, which is going to be, this is just 0. Thus, the trace in V of G in G is independent of which particular G in G we choose, and for every G prime in G, the trace of n G prime is equal to the trace of G minus 1 we see from above, of G prime is the trace of G prime minus G prime is the trace of G prime minus the trace of G prime is going to be 0. Now, since these G prime span the K endomorphisms of V, then the V trace of n alpha is 0 for all alpha and being a K endomorphism of V. And so on n equals 0, which is the same thing as G equals 1. And thus we're done. I think that's the only thing that we have before we go on to solvable Lie algebras. And I'll have to go over our text again, but I'm pretty sure we're going to continue with Bourbaki here. Seems to be the most thorough source going through our solvable Lie algebras. And they do mention the radical, so yeah, I was just mistaken on that front here, which is why I go with my motto, don't trust anything I say. We'll end it here.